What's up, everybody? This is episode 44 of Rolling with Reason. I'm so happy you've tuned in and you're listening to this episode if you're listening to it. Of course, we're going to touch on computer concepts this week because it's all that I've been doing. I did hit the gym a lot this week, so things are kind of heading in the right direction, I think, with that. We'll get into jujitsu here soon, but yeah, this episode is going to be another tech-oriented episode. I hope you guys really enjoy when I kind of go into these deep dives because I think that's one of the reoccurring patterns for me. I think really that for me, doing these deep learning dives and conceptually understanding something and being able to repeat it to the camera or repeat it to other people, like um, at work or just family or friends, like, I mean, it just feels really nice. It feels nice being able to repeat some of the conceptual understandings that I've taught myself. And I think that's one of the maybe biggest dopamine hits for me, is like learning something and then being able to implement it. And so I think that's really awesome and really cool. And I think that's kind of where me getting on here and kind of doing this, I think that's really probably why I like doing it so much. And I think that's why getting on here and kind of expressing that stuff to you guys, telling you about what I'm learning, it's beneficial for me. But some of the things we're learning this week is what's called the Big O notation. Hindsight's 2020. I feel like I probably should have learned this a long time ago. I know I've like seen it tossed around a couple times, but it's in relation to performance. So what I mean by that is, even though we create computer programs, they are fast. Technologically speaking, the computers are so much faster than what they were in comparison to, the early 70s and the early 90s. They are so much faster now, so much more capable. But it doesn't change the fact that if you write code that doesn't correspond to them being um, useful in the term of useful with allocation of their resources, right? If you don't properly have them use the tools and the utilities or the functionality of itself at hand, it's going to perform poorly. And I'm just talking about the computer simply here. There's a lot of different programs and a lot of different means to be able to conceptualize this stuff. One of the big ones for me was connecting it to the how AI works stuff. So maybe to touch on that for a second, one of the things you run into there is a lot of data. And what I mean by that is usually if you're going to train a model, a classical model, even neural networks, usually the size of your feature vector, which is usually one container, and that's usually one item, how many elements or how many items that are within that feature vector is going to be a pointer or an indicator for you as roughly about how much data that you need. And so what that means is if I have a small image and it's 700 something pixels, I'm at least going to want 700 and something samples. So that means I need that many lists, that many containers, that many feature vectors with that many features in it. So 750 samples with 750 features within every sample. That's important, and I think that's a good inclination, or it believes me to be inclined to think that that's where you're going to see mass usage of data. Now, there's also a separation between sloppy data and good data, but we also have some newer techniques that we can use to be able to manipulate that data to give us more samples. And so what I mean by that is something as simple as maybe flipping an image upside down. So even though the image is the same, using data augmentation like that really gives us more leeway into expanding our training data without really changing it, right? So there's not big differences in the kind of outputs that we can see. What does that mean for what I'm talking about, the big O, though, and the performance? Well, if we had 700 something samples that had 700 and something items within them, right? That's going to be a big process to go through. I mean, just imagine if you manually had a page with 750 words on it and you had to flip through 750 pages and look at every word on every page. That for us would take a long time, but thankfully we got computers for that and it makes it a lot easier. But there's a caveat to that. So the big O, there's kind of, I think, 4 or 5 conceptual, kind of like formula formats that you can think about when it comes to computers, and then thinking about that process of going through and looking at data. So O is going to be the process, I suppose is one way to think about it. And then when we say of, we're going to be talking about inside of parentheses. So when we say of, and there's going to be something inside of that of. And for us, that could be a couple different things. It could be a 1, it could be an n, it could be n squared, or it could be log space and then another n. And so what does that mean? What am I saying here? Well, this is a really general thing to me right now, but I know that it's going to connect in the grand scheme of things, kind of like how I was already talking about feature vectors, and you know, that stack of papers, that big stack of papers, right? And so I can use different functions like the big O notation stuff to really evaluate how performance oriented my code is. And so O of 1 is what we call constant time. So in Python in particular, we have names. Those names are also sometimes called variables, or also called labels. But that name is assigned a value. So that could be a number in this case, actually one of the pages of paper in this case, amongst all the other papers, right? But if we wanted to say, let's go to page 53, this would be an instance of constant time. If we say page underscore 53 equals, and then we would say pages, and then square brackets, 53, depending on how it's set up, indexing is a little weird like that, but just know that we're pulling out a specific item out of our 750 page stack, and it's page 53 in particular. What does that mean for us? Well, it's going to be instantaneous. That name variable slash label thing that I was talking about, we use an assignment operator, which is the equal sign. We say that is equal to, and then page 53. And so when we go to access that inside of an algorithm, which is just a sequence of steps that the computer performs to give us or do the things that we want it to do, when we have it run, it just pulls out that value, and it's a constant. And that value is stored in what we would say a point in memory, and we could go deeper into that and talk about the garbage collector, but that's just too much. We don't need to worry about that. All we need to know is that is what we call O of 1. Really easy, constant time. It's indexing, it's pulling out a value, a lookup, a search. It's kind of the same thing. We're kind of in the same ballpark there. And now we're going to move to this next category. Not next category, but this next function-esque time orientation thing. And that's going to be linear time. And that's going to be O of and then N. And so this is going to be when we use what we call an iterative process or an iteration. And so we have these things called for loops within Python. They're exceptionally great. They're used everywhere, realistically, and I think they're understated for the value that they bring. But to keep pushing forward here, the for loop pretty much says, oh, you have 750 pages. Let me look at every single page. So again, that's kind of an example of how we would want to maybe look at something, right? It would take us forever, but we could use a computer and it does it in the fraction of a second. And that would be an O of N. And that's what we call linear time. So what that means is, so for example, single input equals single output. Double input, double output. It just means that it's linear. So in terms of being linear, that means that it's going to go from the bottom left to the top right. Honestly, I don't know how the camera is going to pick that up, so maybe I'll just do this little number and you guys will know what I'm saying. It's positive, positive, no negatives. That's what a linear time evaluation is with O of N. Now, that process, like I said, is a fraction of a second. But let's say we had somebody who wanted to do a nested for loop. And so what I mean by that is this is where things could get a little hairy. So just bear with me here, right? So let's say there's 750 pages in our stack of papers, right? And our list per se. And so we say for every paper in that stack of papers, let's just count. So it would go 1, 2, 3, 4, all the way up to 750. But then let's say every time I'm on a page, I want to loop through the pages again. So I want to count again. So when I go to 1, I then go 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 750. 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way up to 50, 750. And then 3 up to 750, 4 up to 750. Now that is what we call quadratic time. And that's what is called O of N squared. And you can see how drastically in comparison the performance could change there. When we look at something that's linear, right, it's positive, positive. That means it's 1 for 1, 2 for 2, 3 for 3, and so on. But if we have something that is raised exponentially, and so in our case, squared, it's going to be drastically way less performant. And you can see that, if you graph that out and you lay that out. So that's what we call quadratic time. And it's a problem because if you're trying to run through our 750-page set of data, that's going to take, oh my gosh, it could take hours in comparison to what is, I'm not even joking, fractions of a second still. Maybe not fractions of a second, but nonetheless, I think you understand what I'm getting at here. Not being careful with that evaluation of using what are called nested for loops could really put you in a bind. And it could make the difference between having a couple hours to yourself and freeing up a machine or not. And so that type of thing and that type of process is the big O notation. But we still have one more that we want to look at, one more that I want to talk about, and that's going to be O of log n. And so this one's a little more complicated for me, I guess, to a degree. But I suppose the best way to kind of talk about this is that it's when you have what is a sorted set of values, and then you purposefully sort through that set of values to shrink down how many values there are. And so maybe a way to think about this is like, if I can look at a value and then that value is something that I can automatically put into this category, do it. If I can automatically put it into that category, do it. And so you can imagine how if we do that in chunks, then that's going to free up the amount of time that it's going to take to do that process. Otherwise, it would have taken exponentially long, like we were talking about in the quadratic formula. And this is kind of the sweet spot because it means that we can work with vast amounts of data, but we can still do it in such a smaller amount of time. And again, this kind of comes back to how AI works and how the models work. All this stuff connects back to models and things like that. And so let's say we have a model that we train on a neural network. I think we went into neural networks last week. We have the inputs, we have the weights, the biases, the activation functions, which the bias and the activation function reside on the nodes, which are the hidden layers. And the amount of hidden layers we have is based off of the architecture, which then leads us to the sigmoid function in our case, if it's a binary classifier. And that leads to an output. Yes, it sounds super crazy, but nonetheless, that is kind of where all this mass data is coming from and the reason that we need it. And so using the big O notation to really direct us performantly in the right direction is going to be massive. I mean, let's give another example, right? Let's say we have a chat bot, right, that's working on some customer website that we built. If that chatbot isn't performantly set up with this big O notation, it could be the difference between what is a half a second response versus what is 30 seconds. I don't know about you, but as soon as I click on a web page or ask for something to be done through the internet and it's not almost instantaneously done, I just refresh the page. And then you can think about how catastrophically cumbersome that could be as a developer or somebody using the application. It's just not ideal. With that being said, that is why the big O notation is important. That's why I think using it as a means to evaluate your code when you're creating it or when you're moving forward with your processes of building out models, understanding your data to the best of your degree within conceptual understanding, because it can become so large that it's hard to understand. I think that's the big importance, and I think that's why I like it. So I'm learning that right now, and I'm picking that up, and it's going to be extremely useful. If I'm collecting my own data and then using it as a means to be able to make some assumptions or classifications about unknown samples and try to evaluate processes, then that's going to be the way that I do that, and that's going to be the best way for me to really understand that stuff. And so building out websites and integrating these services and just implementing these ideologies and these things into my code, because it's no longer just about building good code. It's not just building code. You have to build good performant code. And I think that's extremely important. And I think that's one of the big steps with refactoring. I think you can kind of have like an easy day where you go through and you can get a lot of programming done. And maybe you don't use a lot of AI tools to help you do it. You kind of do it intuitively. But then you need to go back in and you need to refactor. But you don't want to be producing amount of code that's almost too hard to refactor, because refactoring is really where the bread and butter comes in and where it makes those processes and things you do easier. And so that's kind of what I have on the tech front. But let's go ahead and talk about lifting a little bit this week. Maybe that's part of the reason why I'm having good retention and I'm learning better. Is just because I went out and I did some lifting, and I did it, I think, 6 out of the 7 days this week. I will say I'm still having some body issues, so I had to play that accordingly. But just getting back in the gym, hitting the weights, getting the sweat in, feeling the grind, it's great. It was really great. And so it's really got me wondering how long it's going to be before I'm back on the mats. I want to get back on the mats. The ankle and the toe, there's still problems with the toe, but the ankle is definitely feeling better. It's definitely getting more sturdy as the days go by. But the back's still a little, but we're figuring that out. And we're really just taking our time evaluating how we can really just crush and execute that process so that we're still getting that work in. Um, Other than that, I really don't have that much to say other than like I'm working hard and I'm working on this computer stuff with a type of ferocity that um, I just appreciate like from myself for myself. And I think it makes it easier when I'm working really hard on that stuff to get on here and just kind of just throw it all up on the camera. And so I hope you guys enjoyed this episode. I hope you guys had a great week. This episode was actually a day late too. I'm sure some of the people that watch all the time noticed that it was definitely problematic. But yeah, this is going to be episode number 44 of Rolling with Reason. Thank you so much for tuning in. I can't wait to make the next episode for next Monday. Bye, everybody. Peace.
Thanks for listening. Stay resilient, embrace the struggle, and keep moving forward.